Hello, I'm James Jiang and my partner is Brian Lai, and we will be presenting on search algorithms and Google PageRank. So, the goal of this presentation is to explain how Google, one of the world's leading search engines, utilizes their self-made search algorithm known as Google PageRank to organize billions of web pages in an efficient manner to provide users the most relevant web pages to their searches. And to strengthen this explanation, we will walk through a small-scale example of Google PageRank in the works, along with other methods of organizing web pages. Next page. Starting with some short history, Google PageRank is an algorithm designed by Google's founders, Larry Page and Sergey Brin. It was designed to solve the problem of showing people the most relevant pages when they search for something. The two of them developed this algorithm all the way back in 1996, when they were still in graduate school at Stanford University. Today, Google also utilizes other algorithms to order search results, but Google PageRank was the first and most famous one. And the way it does this is revealed by its name, PageRank. It gives pages ranks. The higher the rank, the higher up a page will be in a Google search result. So say you had a website. Your page has a high rank if a lot of other pages link to it. But it's not only about quantity. What's also important is the reputation of the other pages linking to your page. So ultimately, it's a bit of a reciprocative, community-based factor, but it's also based largely on probability. Sometimes the algorithm utilizes random page jumping to get to a starting point. And with a large enough sample size of randomly jumping around, the most important pages should still have the highest page ranks, because the probability of landing them is high, because a lot of pages point to them. For ordinary small-scale matrices, the eigenvalue decomposition method works fairly well. But for Google searches, which commonly reach into the millions in search results, and thus can hold billions of web pages, requires a more powerful technique, fittingly called the power method. We will be going through both of these methods in the slides to follow. So we'll be going through this specific example shown in the pictures below. The picture on the left is the network graph that we will be using to compute the order of the most important websites. The picture on the right is a specific search query question, which we will be utilizing information extracted from the left picture to solve a specific question, which is, what order should the websites be shown if someone searches for the words anchovy and opa? And we will be doing this at the end, after we have finished analyzing the image on the left. But first, we focus on the network graph. What's going on is that each web page, listed A through L, has outlinks that go to one of the other web pages. The graphics of this is shown here. Not all web pages have the same number of links going in or out of them, which is one of the main factors in determining its page rank. So we utilize these two methods mentioned before, eigenvalue decomposition and the power method, to try to rank these pages based on importance, and then we compare the two methods. And we will show how to calculate what order the websites should be shown if some imaginary search engine user looks up the terms anchovy and opa. Here is the matrix representation of the network graph in the example. The matrix representation is a square matrix n by n, where n is the number of web pages present. It was constructed by ordering the 12 web pages in the rows. If that web page points to another web page, it has its column value changed. For example, web page A, which corresponds to the number 1, and thus is the first row, points to D, which corresponds to the number 4. Therefore, the value in row 1, column 4 is now 1. We continue this process for all nodes in the set of 12 web pages, and this is the resulting matrix. You'll notice that the diagonal entries are 0, and that is simply because web pages don't point to themselves. This representation of the network is necessary for finding linear algebraic components, such as its eigenvalues and vectors, and is necessary for operations such as decomposition. The first step in the eigenvalue decomposition method is making the representative matrix stochastic, meaning that the rows should add up to 1. This was done by counting up the values in each row in the original matrix and dividing each value in that row by that number. You can see the resulting matrix here. The values in the rows that had 2 outlinks were changed to 1/2, and the rows with 3 outlinks were changed to 1/3, and so on. Then we decompose the matrix into 2 matrices, a matrix composed of the eigenvectors and a matrix whose diagonal entries are the eigenvalues of the matrix. The largest eigenvalue that we obtained was 2.23. The problem was with the dangling web pages. Dangling here means that a web page had no outlinks. Visually, in the representation matrix, it had rows where the sum was simply 0. So, modifications to this matrix were necessary to continue using the eigenvalue decomposition method. In order to fix the problem of the dangling web pages, we added artificial outlinks from that web page to all other web pages. So you can see that row 3, which initially had no outlinks, now has a full row of 1s. It was necessary to make this change for the dangling web pages because the previous setup did not give a maximum eigenvalue of 1, which is important in future calculations. In the end, artificially adding values to row 3 will not have a big impact on the order of importance of the websites. And now with the fixed matrix, the same procedure is carried out. After once again making the row stochastic, so that each row adds up to 1, we now have a matrix whose highest eigenvalue is 1. Then we performed the eigenvalue decomposition on the transpose of the matrix G. Samples of the two resulting matrices are shown below. The left is 3 columns of the eigenvalue matrix, and the right is 3 columns of the eigenvector matrix. They actually span 12 columns long, but these are just small snippets to show you what they should look like. The first diagonal entry of the eigenvalue matrix corresponds to the first column of the eigenvector matrix. The second diagonal corresponds to the second column, and so on for all 12 columns. These two matrices are important because a combination of them will create the vector that shows the ranks of the 12 web pages, which we will call the pi vector. So to do that, we create a new matrix called G transpose to the power of infinity, which is the product of the eigenvector matrix, the eigenvalue matrix raised to infinity, and the inverse of the eigenvector matrix. The formula can be seen here. This shows why it was important to have a high eigenvalue of 1. If they were all below 1, then raising the eigenvalue matrix to the infinity power would result in a 0 matrix. A sample of the resulting matrix is shown below that with its first 3 columns. The important thing to note is that since the resulting matrix has identical values for every column, we just chose the first column, which shows the importance of the web pages, denoted by their magnitude. The rows denote the web page, so row 1 corresponds to web page 1, row 2 is web page 2, and so on. After normalizing this vector and pairing them with their associative web pages, and then finally ordering the values from greatest to least, we see that the most important, or the highest ranking web pages, are as shown on the right. 5 is the highest ranked web page, and 4 is the lowest. And if you take another look at the network image, you can see that this ordering makes a lot of sense. 5, which correlates to the letter E, has the highest rank because it has the most arrows pointing in and out of it, as compared to the rest. And subsequently, pages 1 and 4, which correlate to A and D, are the least important, or have the lowest rank, because they have the least amount of activity. Very few links point in or out of them.
Hi, I'm Brian. I'm going to talk about the rest of the slides. A solid math for dealing with very large matches like Google search matches is a power iteration math. The process of power iteration is as follows. You first set the initial pi vector as a normalized vector that is of n length, or as long as the matrix you are working with. For our example, the initial pi will be 12 long, and each value is 1 over 12. Then you multiply this pi vector with your matrix. This result is a new pi vector. You now use a new pi vector and treat it as an old one. You multiply it with your matrix to gain an even newer pi vector. You continue this process till the absolute value of the current pi minus the previous pi is less than some set tolerance you make. This tolerance is usually somewhere around 10 to negative 15. In our case, the loop persists for a total of 62 iterations. Our tolerance at this point was at 9.75 times 10 to the negative 16. The formula for this procedure explained is shown below. So after a total of 62 iterations, we got the following pi vector showing the importance of web pages. And once again, comparing the vector to the network graph, we can see the results are very logical. Web page E is once again, and rightly so, the highest ranked web page. while web page A and D are still the lowest ranked web pages. Power iteration proved to give identical ranking to when we use the eigenvalue decomposition method, and while the individual values were not identical, there were no significant differences that affect the final result in terms of order. We know that the method was primarily used extremely large matrices, but now with the conclusion of this example, we can also say it works fairly well with small matrices. Now to compare the two methods used, both were operations that require the matrix to be row statistic and not have any dingling web pages, although the procedure were very different along with the individual value, we achieved the same result from both. The I vector with their ranking are shown below. The left is the result from the eigenvalue decomposition, and the right is from the power iteration. You can see a slight difference in the absolute value, but the ranking remain the same. The eigenvalue decomposition method is great for a small matrix. The power iteration is useful for large matrices. However, with the last example, we found out that the method was very robust and is able to handle another scenario where you don't have a large matrix. Another thing to notice for power iteration method is that you can play around with setting of the algorithm. In our example, our initial pi vector was a simple 1 over n links for the vector. You could potentially play around with this starting point, while of course maintaining its normality. Another factor you could change around with the power iteration math is the number of iteration. This will depend on the set of tolerance you choose. One potential problem in dealing with such type algorithm is that the hyperlink matrix might not be strongly connected. Just because a matrix might be row stochastic does not mean that it is strongly connected from this problem. This was not the case with our matrix. One way of fixing such problem is alternating the matrix. You can alter your matrix using the following formula to get a new matrix called G tilde. The alternative procedure involves setting a predetermined alpha variable. Typically, this value is 0.85. You multiply alpha by your matrix G. Notice that your matrix should already be row stochastic. This implies that there should be no rows with all zero value. Next, you multiply the complement of alpha to matrix E. E is simply the same size matrix as your G matrix. However, every value is 1 over n, where n is the length of your matrix. Every value is also positive. The E matrix is shown below. The first part, alpha G, can be either 0 or positive. The second part, involving the E matrix, can be only positive. With these two factors in mind, what end up happening is that you are adding two positive components, and so resulting matrix should never have any negative value. The resulting G tilde matrix should also retain the characteristic of row stochasticity. Now, we once again use an eigenvalue decomposition to find a pi vector showing the most important web pages. The new vector showing the order of importance is below. On the right, the one on the left is an old one used for comparison. At the first glance, we see the most important web page remains the same, and for the most part, location of another web pages were wrong where they initially were, but jumbled around a little bit. The adjacent matrix most likely gave us a slightly scrambled matrix because our matrix did not require adjusting. So now that we have finished analyzing the rank of websites, we go back to the problem of what to show a user who searched specifically for anchovy and opal. To do this, we first have to create a turn and darkroom matrix. We accomplish this by setting a different type of features rows. So in this case, entropy is the first row and purge is the last row. The web page represents the columns. We then scan the web page to see which fish they contain, and those values are stored in a row. So for example, web page A has anchovy, grouper, mackerel, pike, salmon, and beta. These correspond to value in the row 1, 2, 3, 4, 5, and 6. We continue this procedure for all web pages, and the image on the right is the resulting turn document matrix. Now we actually take into account of what the person is searching for. Recall that question was what web page should be shown from the top to bottom if someone searched for anchovy and alpha. The way to incorporate this question into our turn and document matrix is by creating a query vector, which is vector that's as long as amount of turn in our matrix. In this case, the number was 15, and we match the correspondence of row to what person is searching for. So entropy and alpha corresponding to row 1 and 12, that gives us a vector that is 15 long and has value of 1 in row 1 and 12. The rest should be 0 because we don't want this another term to be active when we ultimately multiply this vector with our turn and document matrix. The second to last step is creating a vector that reveals which web pages are active when the user search for anchovy and alpha. To create this vector, we modify the query vector with the entire term and document matrix. The resulting vector is shown below. The row that has non-zero value are the web pages that are active. The zero row indicates that the website has no relation with the search. You can see that when someone searches for anchovies and alpha, the web pages that are active are web page A, C, E, G, H, and K. If you take another look at the term document matrix, you see that this result makes sense. For example, the web page D is not active from this search. If we look at D, the list of fish include neither anchovy nor alpha. The same follows for other web pages that are not active. On the other hand, the web pages that are active have either one or both terms in their website. Now we have which web pages are activated when someone searches anchovy and alpha. And we can also have vector that shows the order of importance of website. Now we simply use the information from the two vector. The web pages that are activated should be in the same order of importance as from the pi vector we got previously. Thus, we can include the page E, H, C, K, G, B, and A are the web page in order from the top to the bottom that the user will see. And this is our reference page. And this is all about our presentation. Thank you for watching.